So, did you go through the notes?
Yes.
So, what you understood?
Sir, I studied till how much we left.
Okay, so
Characteristics of three types of
characteristics.
emissions.
Okay, we are going there. So, notes I already gave you in the classroom, right? Notes I
Yes.
uploaded in the classroom.
Hmm.
Mm, it's not here. Yeah, it should be in classroom. Why it's not coming? Okay, we are going back. Yes, this one. So you did before emissions.
Hmm.
We discussed all the detectors last class.
Hmm.
Yeah, so you told that you will go through this again, huh? By yourself. So did you understand everything or you have any queries? Still you have any queries? Hello?
Hello, sir.
Ji,
Till how much you finished?
we did till the modern detectors in last class.
Hmm.
Hmm. So till here you have any queries?
Yes, I was facing some problem in recapping the cloud chamber.
Cloud chamber. Okay, let's go there. In cloud chamber. Okay. So where you have problem with cloud chamber? Yeah. Which one?
Um, the from that in both types part, like from where the trails come out.
Okay, trails. This one, huh?
Hmm.
This one, huh?
The first paragraph. The first paragraph.
Uh, so the chamber contains this one, right? We have there are two types of cloud chamber. One is expansion type and one is diffusion type. The chamber contains a supersaturated vapor.
Hmm.
For example, methylated spirits, which condenses into droplets. when disturbed and ionized by the passage of a particle. So
Hmm.
this one is methylated spirits, alcohol,
Hmm.
yeah, methyl alcohol, uh,
Hmm.
ethanol, you know them, right?
Hmm. Hmm.
So these kinds of liquid is used over there, the methanol, methylated spirits.
Hmm.
Then this one is used as vapor, supersaturated vapor. That means saturation means if you think of our,
Filled up.
yeah, filled up. In our weather, if there is enough water vapor, that
Hmm.
water vapor the air contain, it has the capacity, the air has the capacity to contain the water vapor. If it is too much, uh, then it is completely fill up. That is called uh, saturated vapor, right? Then more than this, if you give the water vapor, it cannot contain. That one will come out somehow, drop down as rain. Okay, or you can understand it from your surroundings that you are feeling too much. Sometimes you see that your body is feeling too much, unwell, like you are feeling, that is called, what can we say, the hot, too much hot, that your sweating is not drying up from your body, right? It's happening if the water vapor is completely taking the place of air. Then no vapor from your body, no sweat from your body can be taken in the air. That time you feel that sticky, your body is sticky, right? with
Hmm.
sweating. So that is happening in the supersaturated vapor, which condenses into droplets. That time it condenses into droplets when disturbed and ionized by the passage of a particle, especially the mentioned alpha particles. So these lines are coming from the droplets. You understand it?
Hmm.
Yeah. So uh, after condensing the methylated spirits, their droplets is shown here. You can clearly see the direction and energy of the particles. Uh, Low energy particles only leave short tails. So alpha particles, uh, how much they have the energy, or the beta particles, how much they have the energy, uh, we can see from here. Is it clear
Hmm.
now?
Hmm.
Okay, then continue where you have problem. Other than
Yeah.
this,
Yeah. Only this one.
only this one. Okay. So you have no other problems. Now we can see characteristics of three types of emissions. We have alpha, beta particles, and we have gamma radiations. So we have three types of emissions. Two two emissions are particles type emissions. Another one is like electromagnetic radiation. So the one which is electromagnetic radiation, that one has the property of light. You can remember the properties of light, right?
Hmm.
What are the properties of light?
Their transverse wave
Mm-hmm.
speed at 300,000 kilometer per second,
Mm-hmm.
and they are part of the electromagnetic spectrum.
Mm-hmm.
And what else?
They
Mm,
don't have any mass. Huh?
hmm,
Light or electromagnetic radiation, they don't have any mass. All the masses are converted to energy. Huh? So gamma rays, they are massless. This is the first thing. And second point is gamma or any light energy, electromagnetic waves. They don't have any charge.
hmm,
They don't have any charge. So
hmm,
if they don't have any charge, they are showing no deflection in the electric field or magnetic field. So are you getting it? If
kinda.
you are if you are uh, if you are giving gamma rays in any electric field, it will not be affected by electric field. It will not be affected by magnetic field. Okay, so gamma rays, this one has these characteristics, and they don't have any mass.
Hmm,
The other two emissions, alpha and beta, they have mass. Alpha, they are the combination of two protons and two neutrons. They are
hmm,
behaving like helium nucleus.
hmm,
So they have positive charges. If they have two
hmm,
protons, that means they have two positive charges, right?
hmm,
And if you think their mass is four atomic mass units.
hmm,
You know, each of the nucleons, um, nucleons are those which are staying in nucleus, right?
hmm,
Protons and neutrons, they are staying in nucleus, isn't it?
hmm,
So they have mass. Already you know from the Rutherford alpha particle scattering that all the masses are centered in the nucleus, right, of any atom. And this is because in the nucleus we are having protons and neutrons. Why we are saying about their mass to compare with beta particles? Beta
hmm,
particles, they are electrons. They have same charge of a single proton, but
hmm,
it's negative. Do you know
hmm.
this?
Uh, Sir, are you talking about positron?
No, we are talking about electrons.
So electron with a plus charge is called a positron.
Yes. So we are now thinking of the beta particles, which one is negatively charged first, then
Hmm,
later on we'll talk about positrons. Now, beta particles, they have negative charge, right?
hmm,
And uh, protons, they have positive charge.
hmm,
And alpha particles are containing protons,
hmm,
no electrons, only
hmm,
protons and
Protons.
neutrons.
Neutrons.
Protons and neutrons, two protons and two neutrons. So alpha particles, they have positively charged. Is it clear? And not
Hmm.
only that, their positive charge is two times greater than beta particles.
Hmm.
So whenever alpha particles is passing through any air or any other, atom, uh, any other atom they are going, then they have the greater ionizing power. Is it
Hmm.
clear to you?
Hmm. Hmm.
The things which have charge with them, they have the ionizing power. So
Hmm.
they can ionize the other things. That's why in
Sir,
that's why
what does
in
actually ionize mean?
okay, ionize means the alpha particle is passing very close to a argon uh, argon atom, right? Which one is neutral? Argon. Can you remember we had in
Rutherford experiment.
no in
Uh,
Geiger Muller tube? We had,
Geiger-Müller. Hmm.
yeah, we
Geiger-Müller.
had argon, right?
Hmm.
So this argon gas is also ionized, hmm, ionized by these emissions, and when they are ionizing, that means it pulls an electron from an argon atom. Huh? Can you
Hmm.
remember this? So
Yes. Yes.
you understand what is called ionizing.
Yes.
Ionizing means to take out electron from the neutral atom,
Hmm.
and making that atom as one ion.
Oh, what? Hmm. Hmm. Hmm.
Is it clear?
Yes.
So
Yes.
alpha particles, you see physics is, it has link with each other, and you will see nothing is contradictory. Huh? If you think in cool brain, then you'll see everything is matching wonderfully. And you see
Hmm.
here also in cloud chamber, alpha particles are best for this. Huh?
Hmm.
So here also we are getting ionizing here,
Hmm.
and that's why alpha particle ionizing best. So
Hmm.
the more you will go, you will feel more confident, huh? Inshallah.
Hmm.
So
Inshallah.
alpha particles, what we are saying, they have two positive charges or double the charges than beta particles. Though its opposite sign, is positive, but it is double, right?
Hmm.
Isn't it? And because of
Hmm.
this strength of this charge, it has greater ionizing power. And beta particles,
Hmm.
they have only one charge. Hmm. They have only one charge. That's why they have also ionizing power, but it is less than the alpha particles. Okay.
Hmm.
Another point is there. Alpha particles, they have lots of mass. Hmm. And here, not
Hmm.
only the charge is working, uh, in your IGCC syllabus, that one you got, and also we had little bit discussion about the momentum. Hmm. That momentum means the combination or the product of mass and velocity.
Hmm.
It's the combination of mass and velocity of an object that is called momentum. So the particle with greater mass, it has more momentum, right? And the particles with greater momentum, it can uh, it can work more on other particles, right? Like if your one friend uh, with heavier mass, like your friend is you and your friend, you are playing football, right? So
mm,
you are very skinny and you are very light, uh, and your friend is very heavy. If your friend is very heavy and he is coming with the ball, and you are trying to pull him or push him, it's not so easy, isn't it? But if he push you, then you will fall down, isn't it?
mm,
So it's also happening because of the momentum, right? So mass is a very
mm,
big factor here. Uh, so the one
mm,
with heavier mass, that one also have some uh, greater ionizing power. Is it clear?
mm,
So actually, both the charges and masses, if we consider, in both cases, alpha particles, they have a greater ionizing capacity, and beta particles, their mass is less. Also, their charge is less. That's why they have less ionizing power. Okay,
mm,
and they both are deflected in electric field and magnetic field, but in opposite way. In electric field, we have positive and negative terminal, right?
mm,
So when you are giving any alpha particles in an electric field, then alpha particles will be attracted by negative terminal, isn't
mm,
it?
mm.
Hello?
Yes, yes.
And the beta particles will be attracted by positive
In
terminal.
the positive terminal. Mm,
Positive terminal. So their deflection will be opposite. Not only that, their deflection, like the way alpha particles will be deflected, beta particles will be deflected more. Why? Because beta particles, they have less mass, right?
mm,
So that's why they can be attracted more, right?
mm,
Because their mass is less, when they are moving with speed, then it's easier for other things to attract
mm,
this with greater force. But alpha particles, they have bigger mass, right? So they will
mm,
be deflected more, deflected less than the beta particles. So this
mm,
way, we are having some ideas, characteristics of three types of radiations. And another thing that uh, here we have gamma, right?
mm,
Gamma, you know about the electromagnetic waves. Among all the electromagnetic waves, gamma has the uh, you know
highest frequency.
uh, highest frequency and lowest wavelength. And
Mm,
because of this highest frequency, they have greatest penetrating power, right?
mm,
So gamma, they can pass through more thicker or more stronger elements or materials, where alpha will be stopped, beta will be stopped, but gamma can go, right?
mm,
They have greater penetrating power. And in between alpha and beta, if you compare them, alpha they have the least uh, penetrating power.
Hmm.
Why they have least penetrating power? Because they have most ionizing capacity. When they are ionizing something, then they are losing their energy, right?
Hmm.
And they can be stopped by a piece of paper, and they can be stopped by the air even after few centimeters air going alpha can be stopped automatically because they have the ionizing power.
Hmm.
And another thing is they have less speed. If you compare
Hmm.
with the speed of light, speed of electromagnetic radiation, then it is 1/10. That means 10% of speed of light. And beta particles, they have 90%. That
Hmm.
means 9/10 of the speed of light. That means
Hmm.
90% of speed of light. Beta particles
Hmm.
can travel with the speed. So beta has the greater penetrating power than alpha. They
Hmm.
can go through the aluminum. They can go through the paper, and they can be stopped only by aluminum foil, right? Ah, beta particles, aluminum particles, things, uh,
Hmm.
and gamma can go through the aluminum, but they can be stopped by only lead.
Hmm.
Okay.
Hmm. Yes.
Yeah, so these all are the characteristics they have what I discussed, and
Hmm.
now uh, you read, then you will find that what I discussed, almost all the things came. Please read
Hmm. Okay.
from here.
Characteristics of three types of emissions. Alpha particles consist of two protons and two neutrons. Hence, it is equivalent to a helium nucleus. It has a mass of 4U, atomic mass units, 4 into the mass of protons, and a charge of plus 2. Alpha particles travel up to about 1/10 of the speed of light. Okay. Uh, Beta particles are electrons emitted with varying speeds, which can be as high as 9/10 of the speed of light. Like electrons, they carry negative charge of minus. Beta particles are much
Minus
lighter
E,
than
minus E, huh?
minus
Minus E means
electrons. Hmm.
it has one value, that is 1.6 into 10 to the power minus 19 coulomb. Okay, so that is in symbol that is shown as E. Is it clear?
Yes, sir. So
1.6
sir,
into
it's charge.
1.6, yeah, charge. 1.6 into 10 to the power minus 19 coulomb.
Beta particles are much lighter than alpha particles. Gamma rays are electromagnetic waves of very short wavelength. They are often emitted at the same time as alpha or beta particles. Gamma rays are massless. Ionization. Ion is a charged atom formed by losing or gaining electrons. All three kinds of emissions are capable of creating ions. Alpha particles knock electrons out of nearby atoms, thus ionizing the atoms. The alpha particles are much heavier than electrons and can simply dislodge them from the atoms. Thus, they have the most powerful ionization ability. Beta particles are less strongly ionizing than alpha particles, but more than gamma rays. It is less likely for a lighter beta particle to dislodge an electron. Gamma rays, uh, gamma rays are the least ionizing of the nuclear radiation as it is uncharged. penetrating particles. Alpha particles are the least penetrating of the nucleus radiations and can be stopped by a sheet of paper. They can only pass through a 2 centimeter of air. Beta particles are more penetrating and are stopped by a thin 1 millimeter sheet of aluminum. The fastest beta particles have a range of a meter or so in air. So what does this sentence mean? The fastest beta particle have a range of meter or so air.
That means if it is only air, ah, it can go for a meter. That means 100 centimeter it can go. Okay.
And then
So, and then it will stop. Why? Because they have ionizing power.
hmm, gamma rays are the most penetrating nuclear radiation. Intensity of gamma radiation can be reduced to half by 1 or 2 centimeter thick lead. And then there is a
So,
table.
is it clear?
Yes, yes.
Whatever we discussed, I think you got all the points here, right?
Hmm,
And nothing new.
hmm,
And at a glance, whatever we discussed, all the things are written here at a glance. Ah,
hmm.
and you can read this alpha, then beta, gamma. This way you read, huh? This table. Yeah, read
Uh,
this alpha.
Radiation alpha range in air 5 centimeter. Ionizing power highly ionizing. Can pass through paper? No. Can pass through 5 millimeter of aluminum? No. Can pass through 5
No,
centimeter of.
no, no. Huh? For alpha, they cannot pass through paper,
Hmm,
and for alpha, they cannot pass through 5 millimeter aluminum. Lead, uh, there is no question to pass. Huh?
hmm.
Then beta, this way.
Beta 15 centimeter ionizing. Yes, no, no.
That means beta can pass through paper but cannot pass through the aluminum.
Aluminum.
Lead, there is no question, it cannot. Then gamma,
Gamma much farther, weakly ionizing. Yes, yes. Almost all or it is stopped. Almost all of it is stopped, but some gets through.
so here we are getting all the characteristics at a glance, right? Now, this one is clear, right? The data or the table is clear to you. We can go to the deflection of radioactive particles, right? The one also I discussed in electric field, how they are behaving. Yeah, continue.
Uh, Deflection of radioactive particles. The behavior of three types of emissions is an electric field. The alpha particles behave like positively charged particles and they deflect towards negative plate in a parabolic path. So, what's a parabolic path?
From the mathematics, there is parabola.
No, I don't know.
Huh?
No, I don't know.
What? You don't know?
I mm,
Parabola, you don't know?
I think I
Parabola is not circular, but is very close to circular path. Huh? That one is called parabola. Okay,
know it's an oval.
like that. Okay, that one is parabolic path. I can show you from the diagram. uh, parabola, huh?
Hmm.
You see the diagram? Hello, Tamjid,
Yes, sir. Yes, sir. Yes, sir.
you can see this diagram, parabola, right side.
Hmm. Hmm.
Hmm? Can you read this in mathematics?
Mathematics, a parabola is a plane curve which is my mirror symmetrically and is approximately U-shaped. It fits several other superficially different mathematical descriptions.
So
Oh, I
at
know.
least
Yeah, I know. Yeah, I got it. Yeah,
you
I know
should
this. I
know
know
it.
this.
You should know it because you should have this in maths.
Hmm.
Okay, now you continue. Yeah.
Where do we go? The beta particles behave like negatively charged particles and are deflected towards positively charged plate. The beta particles show much greater deflections than alpha particles because of their lower mass. The gamma rays show no deflection in the electric field and travel in a straight line as they have no charge.
So
In,
you have the diagram now.
hmm,
Look at the deflection, huh, of alpha.
hmm,
It's going towards the negative, huh, and beta are going to positive.
positive. Hmm,
And alpha and beta, if you compare with them, alpha has less deflection, right?
yes, because of their weight,
Mm,
higher
mm,
mass.
very good. Then beta, in beta also we are showing two types of beta. One has high energy, another one is low energy. High energy
Hmm,
means they have greater kinetic energy.
hmm,
Okay, they have more speed. That one is deflecting less. Huh? The one with
hmm.
less kinetic energy, slower, that one is deflecting more. Then gamma, undeflected.
Yes,
So is it clear?
yes,
Now we are going to magnetic field. Huh? To understand magnetic field, we need some knowledge from electromagnetic induction. That one we left. We don't have that one done. But
hmm,
however, we will try to understand. Hmm. We have one law or rule, that is Fleming's left hand rule. You should make your hand ready, left hand ready. Is your
hmm.
left hand ready?
Yes,
And you should fix your thumb, your first finger, and your second finger the way they are showing. Huh? You set in a way that in between the thumb and first finger there is 90 degree. Again, in between first finger and second finger there is 90 degree.
hmm.
Are you setting that way?
Yes, yes,
Okay, so your first finger is showing magnetic field direction, and magnetic field means uh, you know about magnetic field that the magnetic field we are getting from north pole to south pole, right? North pole to south pole.
Hmm.
So if it is north pole to south pole, like in your magnetic field, you are getting the direction this way. That means north to south. Here we have north pole, here we have south pole. Is it clear?
Hmm.
So this way we will do. And current direction in the second finger this way. That means if your current direction in this direction, that means positive to negative. Huh? Here is positive, positive to negative. Okay, is it clear?
Hmm.
So this principle we will use here. And another thing we know, that is conventional current flow and electron flow in a circuit. If we have one circuit here, you know this, you finish current electricity, that's why you know this. That means your current will go from positive to negative, right? It is I. And your electron direction is from negative to positive, right? Hello.
Yes, sir.
Electron direction is from negative to positive. So it's clear now. Uh, if you are clear till now, then we will start our discussion about alpha, beta, and gamma particles, gamma radiations behavior in magnetic field. So here uh, they are saying this one is a magnetic field, the dotted lines.
Hmm.
Dotted lines are magnetic field into the page. Hmm?
Yes, sir.
So how you will place your first finger towards the page, right? Inside the page. If it is into the page, are you clear what I'm saying?
Yes, sir.
Okay, but they are saying no. It's out of the page. The dotted lines are out of the page. If it is cross lines, some of the places. Hello.
Yes, sir.
Some of the places you will see dotted lines, and they will tell you what the dotted lines are meaning. And some of the places you will see cross lines, this way cross. Other than this dot, some of the places you will get cross, 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 cross. So here they are saying magnetic field is coming out of the page. So you place the first finger out of the page. Is it
Out
clear?
of the page.
Yes, yes, out of the
Hmm.
page. You place your first finger out of the page. If it is set, then I will start.
Yeah, done.
Okay, very good. Then your first finger is coming out of the page. You maintain that one. What I said at the beginning, that you maintain 90 degree with the thumb and first finger. again with the first finger and the second finger. You will maintain
Hmm,
this
yeah.
90 degrees. Okay.
Hmm,
Now you check that your alpha. First, we are talking about alpha, right?
hmm,
Alpha is going from left, so it is showing the direction of positive to
hmm,
negative, right?
hmm,
It is showing the direction of current, is it?
hmm, hmm,
Yeah, now you will keep keep your first finger the way it is, and only you will change the direction of your second finger uh, towards the direction of alpha,
hmm.
towards the direction of alpha, is it?
Towards the
So
direction of
alpha, yes,
alpha.
that means it is showing the direction of current, right? Positive to
Yes.
negative. So you check now, where is your thumb going? It's going down, right?
Hmm,
Your thumb is going down, right?
hmm.
Is it, or you have still confusion? Your thumb is going down, or
Kind of.
huh?
It's a bit slanted.
Yeah, your thumb should go down now.
No, it isn't.
Hmm? Your
No, sir, it isn't.
you are you your first finger is towards you, right?
Hmm.
Your first finger is towards you, and your second finger should be right side. You maintain 90 degree.
Hmm.
Okay, then your thumb should go down. Is it going down?
Should. No, sir.
Hmm.
Sir, should I turn on the video?
Yes.
Okay.
Left hand, not right hand.
Yeah, left hand, left hand. So, how do I do it?
Hmm.
So in the beginning, it was like this.
Hmm.
Uh, so
So first finger should be towards you. I told you, just make it opposite. Towards you. First finger should be towards you. That is out of the page. Towards you. Towards
towards
you, not
me,
towards
like
me.
this.
Yes, 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 yes. Now
So
it's
I thought this one's the first finger.
oh, this is thumb. You see
You're
this
saying
one.
first finger, so
Yeah, first finger is this one.
okay, okay.
That is index finger.
I
First
guess
finger for field.
name.
Now it's okay. Your
Hmm.
first finger should be towards you. That is field, magnetic field. Towards you, not right side. First finger towards you. Yeah. Then
First,
second finger
like this.
should be no, no. You took the second finger towards you. No.
Sir, say thumb or index finger.
Okay, index finger towards you.
Okay, index finger towards me.
Yeah. Then your ring finger to the right side.
Ring
Yeah,
finger to the
make it
right.
upside down. Make it upside down. No, no, no. You don't move your finger. Just keep that way.
Ah,
Only you make your hand upside down. Yeah, this way.
oh,
Yes, correct, correct, correct. No, not this way. Opposite way. Your
opposite way,
your
I guess.
your ring finger should be towards right.
Like,
You maintain that
ah, like this.
your index finger is towards you.
Okay, I maintain my index fingers towards me,
Yes,
and
then and make the ring finger towards right side of you.
like this.
I don't move the finger. Don't move the finger. Move the hand. Keep the
Oh, move the hand.
okay. Yeah, yeah. Then your thumb will go down.
Hand.
No, no. Your index finger should be towards you.
Sir, you show me.
Okay, I'm showing you. Just give me a minute, huh? I'm showing you, and also with me, you should do.
Hmm.
Okay, you should do also with me. Now, yeah, check, huh? The first finger is towards me, huh?
Hmm.
Okay, and you see the thumb is going up, huh? What I said,
Hmm.
I keep the first finger or the index finger towards me. I'm not changing it, huh?
Hmm.
You can see it uh,
Hmm.
from the sideways. Okay, I'm just moving my place, then you'll understand it. Yeah, you see, the
Yes.
first
Yeah.
finger is towards me, huh? And I'm
Towards
making
me.
the,
Hmm.
yeah, I'm making the second finger or the ring finger right side. You see, I am not changing the first finger or the index finger uh, from my side. I am keeping it there,
Hmm.
just changing my hand this way. Okay, you see,
And
it was left side. I made it right side now. You see, the thumb is
okay.
going down. The thumb is going down, right?
Hmm.
And thumb is showing you the direction or the deflection, the force,
Hmm.
thrust. Thumb
Hmm.
for thrust. Okay, got
Hmm.
it? And that's why the alpha
Yes.
particle is going down. Got it?
Oh. Okay. 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 Okay.
That's
Okay.
why the alpha particle is going down.
Got it. Got it. Hmm.
Got it now?
Hmm. Hmm.
Okay, the beta particles are of opposite charge, isn't it?
Hmm.
So if you consider the direction of your current, then it will be opposite, right?
Hmm.
Isn't it? That's why, yeah, you just
Hmm.
change it oppositely. Uh, it's coming, the thumb is up now, right?
Hmm.
So the beta particles are going upwards. That's why. Is it clear?
Yes. Kind of clear.
Yeah. Right. I think this is dark. Oh, there is no electricity in my house. That's the problem. I cannot
No problem.
switch on the light. Uh, Now I am using the charger light. Huh? The
Hmm.
charger light, you see. It's clear now?
Yeah. Kind of clear. Hmm.
Yeah. So it is our position. Huh?
Hmm.
Electricity came. It is our position, you see. Okay. All the fingers should be 90 degrees. Huh? This is
Hmm.
the position. Huh? You cannot move the position of the finger. You can only move the position of your hand. That's the
Wrist.
condition. Okay. So it is
Hmm.
out of the page. That means your first finger, the index finger, should be towards you, right? You should fix
Hmm.
it first. Then you change. Now our direction of, you know, here you can see direction of our ring finger is working uh, opposite than before in beta particles, right? That's why the
Hmm.
thumb is going up.
Hmm.
Is it? Is it clear?
Hmm. Hmm. Yes.
You can also check. And for alpha particles, it was like that. Just the change of direction. You see, our second finger. And this is our second finger, so we change the direction of it, opposite, and our thumb is going down. Okay, is it clear? It is alpha. You see, the first finger is still
Hmm.
towards me.
Hmm.
Okay,
Hmm. Hmm. Yes.
out of the page. It is out of the page. First finger for
Hmm.
field, magnetic field. Second finger
Hmm.
for current, and the thumb
Hmm.
is for thrust. Okay,
Hmm.
That's mean force or the deflection.
Hmm.
So is it clear?
Yes.
Okay, done.
Yes.
So this way our magnetic field, the field, uh, we have electric field, it is very easy to understand, right?
Hmm.
Magnetic field we had to understand from Fleming's left hand rule, and Alhamdulillah we are done with Fleming's left hand rule, and it will be easier for us when we will discuss the electricity. Okay, we have another rule, Fleming's right hand rule. That one we don't need now. We will discuss in when we will discuss the generators. Okay,
Hmm.
is it clear?
Yes. Yes. Hmm.
So now the last one, gamma, you know already that gamma does not have any positive or negative. That's why gamma will always undeflected in magnetic field also.
Hmm.
So if all the things are
Hmm.
clear, then you just go through. Huh? You just go
Hmm.
through this one. Huh? Read, read, please.
Um, uh, so from nuclear reactions or
No, no, no.
from
The alpha particles from the.
okay. The alpha particles and beta particles are deflected in directions given by Fleming's left-hand rule. Alpha particles are positively charged. The direction of movement of alpha particle and be considered as in the direction of conventional current. Uh, Therefore, the force on them must be towards the bottom. Beta particles are negatively charged. The conventional current flow is in the opposite direction to the movement of beta particles. Uh, Therefore, the force on them must be towards the top.
Mhm.
X, Y, and gamma rays are not affected by magnetic field and they travel in a straight line.
Yeah, then
The,
continue this part also
the
the
figure
figure.
above illustrates the behavior of the three types of emission in a magnetic field. The magnetic field is coming out of the page as denoted by the dots.
So clear everything,
Yes, got it.
and we have here slow beta particles and faster beta particles like before. Huh?
Hmm.
That one is clear. Now nuclear reactions. Huh? Nuclear reactions. Should we discuss today or next class?
No, sir, I'm fine. I want to discuss today.
Okay. Okay. Then we can continue this one in nuclear reactions.
Hmm.
We have we have some reactions related to nucleus. Okay, and we are dealing with the nucleons, that means protons and neutrons. And in nuclear reactions, we are having the element changes. You know, the elements, uh, they are maintaining the atomic number or proton number. If it has 6 protons, then it is carbon. Are you listening to me?
Yes, yes.
If it has 7 protons, it is nitrogen. If it has 8 protons, it is oxygen. Isn't it? Hello?
Yes, sir.
Yeah. In
Hmm.
chemical reactions, what happens uh, if the electron number is changing, right? From the outermost shell, like you are getting carbon dioxide. The carbon dioxide we are getting, there is only uh, sharing of electrons between oxygen and carbon, right?
Hmm.
Isn't it?
Yes. Hmm.
But from their nucleus, we are not having any change. So even after being carbon dioxide, they are still having the property of carbon and oxygen, right? Uh,
Yeah.
as per elements. But in nuclear reactions, if we are thinking of carbon 14, okay, so what is happening in carbon 14? Uh, Carbon 14 is having 6 protons and 8 neutrons, right? 8 neutrons. We are having 8 neutrons, right? And we have 2 extra neutrons than proton. Do you agree?
Yes, yes.
So they will go for radioactive emission. And carbon 14 is radioactive, and 1 neutron will emit. 1 neutron will break down, and it will be 1 proton plus 1 electron. That is beta particle. So when we are getting 1 proton uh, more here, then is it working as carbon anymore, or it is becoming to nitrogen?
Becoming nitrogen. It's becoming
Nitrogen.
nitrogen.
So element is changed, right? The element is changed. Is it clear?
Hmm.
So in
Yes, yes.
chemical reactions, we are having only transfer of electrons. Element remains same, but in nuclear reactions, we are having element changes.
Hmm.
So got the differences between chemical reactions and nuclear reactions?
Hmm.
So this way, there is some differences between chemical reactions and the nuclear reactions. Nuclear reactions, we are not only getting beta particles, we are also having, for greater or heavier nucleus, we are having alpha particles, because in heavier nucleus, we have the difference of neutron number and proton number bigger, right?
Hmm.
So that time, if you are having 2 protons, 2 neutrons, 2 protons and 2 neutrons together, that time we are having alpha particles, right? Hello, hello, Tamjid, Tamjid.
Yes, sir.
So there is possibility to have alpha particles also, right? In heavier atoms,
Hmm.
heavier nuclei. We are having also gamma radiations over there. So this way, in nuclear reactions, we are having element change, we are having alpha particles, we are having beta particles, we are having gamma radiations. Okay, and
Yes.
all this have explanation how we are getting the alpha particles, how we are having the gamma particles, gamma radiations, and how we are having beta emissions. All these have explanation. Beta already you understood, right? The one we
Yes.
are getting as electron, that is beta particles. Okay,
Hmm.
hello.
Yes, sir.
Okay, now
Hmm.
you please read this part, then you get some more ideas. Huh? Please read. Hello.
Chemical reactions
Hmm.
result only in the transfer of electrons. Element remains same. But in nuclear reactions, the nucleus in the reacting element and the produced element are not same. A nuclear reaction is a reaction that changes the mass of the nucleus. Nuclear reactions occur both in nature and in nuclear reactors. In nuclear reactors, the standard nuclear reaction is the decay of uranium-235. The super heavy elements in the periodic table, that is to say, those with atomic numbers exceeding 83, undergo alpha decay to reduce the number of protons and neutrons in the nucleus of the atom. An example of alpha decay would be the decay of uranium-235 and into thorium-231.
Okay.
Elements with a high neutron to proton ratio undergo beta decay, in which a neutron is changed into a proton and electron. As the entire process takes place in the nucleus of an atom, and the nucleus can only contain protons and neutrons, the electron that is generated is ejected from the nucleus as beta particle.
So here we got thorium, right? Thorium
Yes.
90. That means here we are losing two protons when it's going from 92 to 90, right?
Hmm.
Then we are having here mass number 235 and here mass number 231. That means we are losing two protons and two neutrons, right? Altogether, and that one is alpha decay. Okay,
Hmm.
is it clear?
Yes, yes.
Okay,
Hmm.
then we have another example where we have uranium 92 235. Then we are having beta decay. We are having neptunium 93. The mass number remains same. The reaction already I showed in the previous page, right? That one is one neutron is converting to one proton and one electron. So if one proton increases, that means the atomic number changes, right? It's becoming 93, and when it is 93, then it's no more uranium, it's becoming neptunium.
Hmm.
But the mass number same, you are losing one neutron, but you are also gaining one proton. So the mass number remains same.
Hmm.
So if there
Yes,
is
sir,
any
but
beta,
can you say me one more time, when does alpha occur? Alpha decay occur, and when does beta decay occur?
okay,
And
so
mixed up.
if if you think this one, huh? Uh, like we are having here one proton.
Hmm.
Azan is going on, huh?
Hmm.
Just one 2 minutes, huh?
Yes. Hmm.
Azan is doing. Now, what you asked about the alpha, right?
Hmm.
Hello.
Yes, sir.
So this way, we are not only getting only one beta particle. There might be more reactions. We are having more neutrons. Here we have the difference of neutron and proton ratio. 235 minus 92. How many can you subtract?
Yeah, 30, 43, 143,
143. So 143 minus 92.
143 minus 51,
How much?
51,
20. How much?
51.
Okay, 51. 51. So we have here how many neutrons extra? 51.
Hmm.
So out of all these, neutrons, only one neutron will not work. There might be some other neutrons are also doing this. Proton plus electron. So if, for example, one of the neutrons is changing it to neptunium, but other two neutrons they are changing to proton and electron. So uh, how many protons we are getting here? Two more protons, right? Hello,
Yes, sir.
two protons are here, and how many neutrons are left then? 49. If two neutrons are working again, then how many neutrons are left? 49 neutrons, right?
Hmm. Hmm.
So for out of these 49 neutrons, if you think that two neutrons are joining with this one, these two protons, so they are producing alpha particles, right?
Hmm. Yeah.
This way we are getting the alpha particles. So here we have enough in neutrons to make more, beta decays and alpha, right?
Hmm. Hmm. Yes.
We can make a lot, right? Or there
Hmm.
is possibility to make a lot.
Hmm.
Is it clear?
Yes. Hmm.
Okay, so this one is the way to produce the alpha particle. And now, how the gammas are coming? Okay,
Hmm.
how the gammas are coming, we are going to discuss that one. Then it will be clear to you, right? Then how alpha, beta, and gammas are coming.
Yes. Hmm.
Look, we have here technetium 99. Uh,
Hmm.
uh, technetium. Uh, Here we have technetium 99, and we are saying uh, it is M. It is written here M, right?
Hmm.
Hello.
Yes, yes.
So this M is standing for metastable. Metastable means
Ion.
which in terms of an atom, ion or atomic nucleus means that the atom is at an excited state. Okay,
Hmm.
so
Hmm.
this one is decaying gamma. How it is decaying gamma? We are going to have some discussion from here also. Uh, this one, uh, we we know when from we are going to the parent nuclei to daughter nuclei. We are having here 92 protons, and here we are having the 93 protons, right? Hello.
Yes, sir. Hmm.
So when we are having this 92 protons and we are having a 93 protons, uh, we have here mass number 235. Here we have mass 235. We have one here neutron extra, one you have here, and neutron less, right? One proton is more. You
Hmm.
know that there is a little bit difference in between proton and neutron. You know that, right? Mass of neutron and proton.
Yes, yes. Hmm.
Look at the beginning. I'm going for more easier explanation. You see here, here. Mm, no, not. It is exactly given later. The mass of protons and neutrons.
Wasn't it in chapter 27?
No, 27. Do you think so?
Yes, I think it's in 27.
Okay, wait then. Wait. Just here we are having this one. Yeah, here also we have, huh? This one, huh? Look, here we have combined mass of four hydrogen nuclei is 6.693 into 10 to the power minus 27 kilograms. Huh? Why it is? Because four hydrogen, they have only protons, right? Hello?
Yes, sir.
They have only protons. So if you uh, make the sum of their mass,
Hmm.
then it is coming like this: 6.693 into 10 to the minus 27 kilograms. And from this four, we are getting helium, right?
Hmm.
And helium has two protons and two neutrons. So their mass uh, of the one helium is coming 6.645 into 10 to the power minus 27 kilogram. It's
Hmm.
coming because there is some mass difference between protons and neutrons, right?
Hmm.
So here we are having some extra mass. and here we are having some extra less mass. If you subtract, then you will get the difference, that is 0.048 into 10 to the minus 27 kg. So when we are getting from the parent nuclei to daughter nuclei, here in nuclear fission, that is the reaction, you see, also here we are getting this one, parent nuclei to product nuclei. That time also we have the change in number, right, in proton
Yes.
and neutrons. So that time we are having the mass defect. Because of this mass defect, we are having the energy emission. Uh, we are having this energy emission. You see, here we are getting technetium, this one as metastable. That means before this technetium, it was another element. Uh, do you understand what I'm saying?
Mhm.
The element was different and it's turning to now technetium. So in between this, turning to another element, in the middle it's in meta state or meta stable state, and it is because of that mass defect. We got the equation here, E equals mc square, right?
Mhm.
When the mass turns to the speed of light, that is turning to energy, right? The mass is getting the speed of light. That time mass is completely turning to energy or light, electromagnetic radiation.
Mhm.
Is it clear?
Yes.
So that one is our gamma emission or gamma decay. So this one coming from the mass defect, like a proton is converting to neutron, neutron is converting to proton. That time we have a mass defect or mass difference between the product and the parent nuclei, and because of this mass defect, we are having the energy. That energy is radiated as gamma emission or gamma radiation. Is it
Mhm.
clear now
Yes.
how the gamma radiation is coming?
From the technetium, like from that M,
Not technetiums
from the
is
energy
not
which is
only this one is the converting from technetium to technetium. It's before this one, it has another step. Okay, before this one we have another step. Okay, and from that step to this step is coming. That time it's coming metastable. Okay, and
Mhm.
this metastable is coming because of this mass defect.
Mhm.
Is it clear to you?
Yeah, yes, now got it. Mhm.
Like this one, neptunium. Neptunium might be a is 235 m. Okay,
Mhm.
and it has some mass defect,
Mhm.
and it will convert to 235 neptunium to 93. Okay, and
Yeah, and the
you
energy
understood it
release.
now. Now
Yes.
is it clear now?
Yes.
Okay.
Sir, I think so. We can leave it till this much today for today.
Okay, okay. We can leave it here. Thank you so much for your cooperation, for your attention, and for your enthusiasm. Okay. So what we learned today, just sum up, then you finish.
Um, I learned how is alpha, beta, and gamma decay occurring,
Hmm.
and the deflection of alpha, beta, and particle, alpha, beta, and gamma.
Hmm. Then Then
and
what?
how this when and in case of an gamma decay, how this how energy is how energy is released due to mass deflection, and yes, this.
Okay, so we actually learned at the beginning the characteristics of alpha, beta, and gamma, right?
Hmm.
And from there we got many things. Alpha's charge, then alpha's mass, then alpha's ionizing power, beta's ionizing power, gamma's ionizing power, their penetrating power, right?
Hmm.
All these things we got, right? And why those are different, also those things we explained,
Hmm.
discussed, isn't it? And after that,
Yes.
we had the difference between nuclear reaction and chemical reactions,
Hmm.
right? Those things you missed, isn't it?
Oh. Hmm.
And finally, we got how we are getting alpha, how we are getting beta, and how we are getting gamma radiations, right?
Hmm.
Okay,
Yes, yes, got it. Hmm.
okay, that's all for today. Now you try, huh? Try the worksheet as much as possible until
Hmm.
the next
Okay.
class. Okay,
Okay. Okay.
thank you so much.
Welcome.